Did you find yourself over the weekend? Recollect, review, like think about things you've learned and where you want to go. Ready for the next chapter? Maybe? No. It's still Monday. But it's Monday afternoon. Like, shook off all the cobwebs this morning. Awake again. Had your third Monster Energy by now. No? They are expensive, right? Yeah. I'm more of a coffee drinker. I don't drink energy drinks anymore. But I do love my coffee. Very particular tastes. So the quick logistical update. Quiz number 1 is on Husky CT. There's a PDF based on what we talked about kind of 2 Fridays ago, and then we briefly went back over. I just wanted to at least get a check. It seemed like no one felt that the content was out of reach. So let me pull this up, do a tour. So coming down to module 1, quiz 1, there's like the readings, kind of what stuff we did, and then now there's this new item that says quiz 1 that is a PDF of, like, I tried to kind of capture the things that we talked about and like what we felt like we were capable of demonstrating at this point in our dynamics learning journey. And this one you can do on your own time. It's just a time for you to try something just on your own. Like we've done some homework problems. We talked about what we're capable of at this point. Now do this, and then it's due tomorrow. If you can't get it done by tomorrow, then like put a note that says, hey, it's forthcoming. Let me know how long it'll take, or if there's like some other question about it. If like I don't understand why. What is that weird squiggly A thing? That's an alpha. Alpha is 5 degrees. But now we can jump right into, we did our project 1 proposal on Friday, and the next thing is jumping into constrained motion, like thinking about what is motion, and when we start adding constraints to it, how does that change how we define it and how we talk about it? And then also like how do forces work when we have constrained motion? So a lot of times this is called like inverse dynamics. So you know what you want to do. I know I want to accelerate this thing at 1 meter per second squared. I know it's 1 kilogram. And so now I can say F equals 1 times 1. I need 1 Newton of force. But it gets more complicated as we start like rotating things and pinning things and adding other things like pinning, sliding, rigid attachments, Grubler counts, all the fun stuff. But we can do all sorts of cool stuff like this.
Versatile inverse kinematics formulations for relative groups, including arbitrary parallel and series parallel hyperparallels.
I'm just skipping over. Like robot motion is a lot of times like this inverse kinematics. Like you know what you want the robot to do, but you need to tell the motors how much torque they need to apply. This would be like an example of, I want to move the hips there. What do the legs need to do? And on Friday, some people were kind of talking about like, how do we describe walking? How would I create a project about running or create a prosthetic of a leg? And you can see like it gets complicated quickly, but we'll cover some of the basics. Oh, why did I do that? So our first question, homework 1, question 1. We have a flywheel and we know how fast we want to accelerate it. but the question is, how much force do we need to apply? So this is kind of like two ripcords pulling on this flywheel. And a flywheel is just a fancy name for like a big disc, like something that stores rotational energy. So we're trying to start this thing up. Typical problem in starting a car, your car starter would be doing this kind of work. Like when you hit the key or you hit a button, depending on what year the car is, usually keys for most people. Then you hear that, it's a starter spinning, creating torque to actually get the engine flywheel moving, and now you can combust and move forward. So we know what we want it to do, but we don't know how to do it. That's kind of this inverse kinematic problem. So I know I want it to do this, and I know I want this to be 50 radians per second squared. And I know that 25 newtons, I is 0.5 kilogram meter squared. So 25 newtons, okay. Only to the left? Or 12? How did you get there? What was your?
So we know that this is after design the rotation, so it's basically F equals I, and we know that we want A to 50, and we have I, so it's basically 25 times 50 is 10,000. But we have two sources of that, so it would each F would be either 25 or 12.
So it's definitely like on the right idea, because force is always motion. Force is always like a change in momentum. But I wrote out like right now what units we're dealing with. So here, if I have a newton is kilogram meter per second squared, like a mass times an acceleration. That is newtons in terms of like base units. Now I is kilogram meter squared. And then alpha is 1/2 squared. So we're missing a meter in there. Like somehow we have F equals I alpha, but no, like we have a meter on one side and a meter squared on the other. So we're missing something in this definition. But we are definitely like on the right track, and that's a good start. I like it. What do you think? You already know what's missing? Okay, yeah. Let's see. Yeah. Torque instead of force. F times, yeah, like some kind of distance, right? F times R. Is it FR? So just R times F. That'll give us the right units, right? R times F, like that. What did we skip? We jumped right into an equation, but we skipped something. Cross product, free body diagram. At least this is, I always start at free body diagram. You gotta start with free body diagram. Yeah, but there's no constraint forces. We didn't like sum up moments. Yeah, like there are forces drawn on, like it's pretty close to a free body diagram, but we didn't formally say this is free body diagram. It's equal to motion. So yeah, I don't know. Some people can just like, if you see the same thing over and over, then you just kind of skip that free body diagram step, jump right into an equation. but 9 times out of 10, the first thing that another engineer will ask you to do is show them the free body diagram. Like, where are you getting this equation? How are these forces being applied? Which direction are they going? All those kind of things like that. But anyway, all right, so try that. And whoop, that is a terrible circle. All right, so we do have these two forces, right? And it could move left or right, right? What else do we have? What else is your diagram? I know you didn't want to. You didn't want to draw free body diagram. What do you do? Gravity? You could add gravity, or it's rotating pretty fast. Like a lot of times, flywheel like that, it doesn't matter if it's like laying flat on the table or standing upright, because the forces that we're applying are a lot bigger than the gravity forces. And hopefully, as a flywheel, it's not moving left or right. So there's got to be something preventing gravity from affecting it. Like some kind of constraint force, right? Like an Ry, an Rx. Because if I only had one force pulling on it, it shouldn't roll with me. At least that's what I think. That if I pull on my lawnmower, the lawnmower shouldn't come at me. But I don't know. Maybe I'm just old-fashioned. But I don't like lawnmowers running me over. But I have almost had a lawnmower run me over when I was in high school. Like as a like groundskeeper for Rocky Neck. There was no off. Normally there's the off switch. It didn't work, and they told me to mow like a slope, and I slipped on the rocks, and the lawnmower came after me. So I rolled out of the way, and then people on the beach were like jumping out of the way, having a picnic. It was a disaster. But anyway, when you start, it didn't help me. It helped you after. What else are we doing? Because right now all I have is that we have two equal opposing forces. MAX is 0, MAY is 0. So what's missing?
A direction.
What kind of direction?
Like where it tells you what's positive and negative.
Yeah. I mean, here I'm saying like right is positive, up is positive. So those, but we're missing something like core. And we started to get to it in that first equation because we jumped right into summing forces and setting it equal to changes in momentum. So we started to get there right away. But acceleration? We have like linear acceleration on here because we have AX and AY. So with those two, I can describe any kind of planar motion. Going this way, that way. There's something else missing. Which one? Mass. It has mass. So we have like MA. We don't have radius in there. Yep.
Is there any friction?
I mean, we could say there's friction, but usually it's pretty low, like some kind of ball bearing. Otherwise, again, it's not a very good flywheel. It's like clamped down really tight. It doesn't rotate very well. Do you know what's missing? No. Yeah. Moment is, so moment is on this side. Like, so the And then on the other side, we have to describe like what does a moment do to that object. And the main thing that it can do is like rotate. So there's a resistance to rotation called inertia, like the moment of inertia. So I can say that this is like an I alpha, that rotation takes torque, and the amount of torque that it takes to create rotation is I alpha. Same way that we have like a force creates motion through MA, I alpha is our like sum of the torques is I alpha. And like if you're ever interested, we could spend half hour in like an office hour session of deriving how I relates to infinitesimal DMs located throughout a body, but for now it's a table lookup thing. We can always look up for a given shape, this is the moment of inertia, and it's always some factor of like mass times meter squared object. But roughly it's describing like how much of the mass is away from the center versus in the center. It's like the standard deviation of mass. So now I have sum of the forces. I have 3 equations for every problem. There's always every like planar problem. Sum of the forces in the x is max. I have a force right and a force left. And then I have Rx, but F minus F is 0, so Rx is 0. Sum of the force is Y, Ry plus nothing is May, but that's all, it's a reaction force, so unless there's already acceleration happening, then Ry is 0. What does my moment look like? How much torque is there? We know that it's equal to I times alpha, but what are the forces? What are the torques there? How much? Yeah, so we know how big it is. Yeah, maybe we can write down the givens. 0.1, so R is 0.1. These are like horizontal kind of forces. 0.1. Negative 250. Okay. Maybe 5 vector. Yeah, maybe. Okay, yeah, minus. Okay. So I saw this so far, like minus RF, because this top force is R, and if you use like right hand rule to describe positive, it's creating a negative torque into the page. And now down here, R times this one, also creating a negative torque into the page. So negative RF negative RF. So now I've got negative 2 RF is I alpha. And we almost, like, we were pretty close, right? By just saying there's a radius, there's a force, set it all equal to moment. The only thing that we were missing was really like we have a force couple. So total torque was 2 FR or F times D, right? Like if you have a couple, you need total distance from the coupling moment. Now we can plug it in and say like F is I alpha over 2R, and then I think, what was that, 0.5? And 50. Like that. So half of 50, 25, half again, 12.5, and then times 10, 125. Sounds good. Oh, and I dropped, so these negative signs like end up dropping out because again, this thing is rotating this way, so like into the page. So when it's rotating that way, it's a negative 50, and our total torque is a negative 2 RF. So negative, negative, all positive scalar values. Not too tough, right? We're in it. Now we got like rotational motion, rigid bodies. This is all like the advanced dynamic stuff. This is what you get paid the big bucks for. So if you can do this, then we're on a roll. All right, so we have the system, and like this bottom block, really it connects across. I didn't want to. So there's a constraint that this point always has to move left and right. It can move anywhere at once, but it's always got to be on one plane. But we have this moving mechanism. General structures like this is called like a slider crank. One thing slides. Here it's rolling, but sliding, rolling. It's on like one plane, on one line of motion, and then the other thing is like cranking. Sometimes it goes around in full circle, like a piston and a crank. But this is a structure called a slider crank. So first question about a slider crank like this, as it's moving, is I'm applying a force down on it. So like, let's say I'm trying to lift a car, like, because this is how like a car jack works. It just has two of them to make a, yeah. So, but it's same idea. You could make a car jack that's a slider crank. So one slides, the other one's pinned. So let's say I'm trying to lift a car. So the force on top of it is a constant force. And I want to know how much do I need to press on it with R? Like how much am I pushing on it? Either with a roller thing, like something creating force. And the first question is more of like a, like without, you can do math, you can math your way through it, or you can kind of think about it. Is when, at what angle, like when is this thing going to have zero force? That the amount of force that I need to push on it is zero. When is R zero? For what angles? Yeah. 90 degrees? Which one's 90? So this one, what do you mean? How high?
Force this kind of force angle to our angle theta 1 theta 2.
Yeah.
Where are we starting?
So in this case, what we're doing is a process called quasi-static. And in quasi-static analysis, the only thing that matters is like what you're considering, like as if it's like frozen in time. So it becomes a static problem, but it is a moving system. I don't know if that's like kind of a different answer to what you asked, because your question was how high does it need to go?
How high are we already?
Right now we're at 30 millimeters high, and we could go higher or we could go lower. So the first question is like, when is r equal to 0? Theta 1 is what? Theta 2. Like this. Like L1 is 90 degrees. And then L2, how do you get that triangle to finish? So you want both of them to be 90.
So like if it rolls in, so theta 1 is 90 degrees, so is theta 2.
Like that?
Theta 2 is off the ground.
Yeah. Yeah, so we can't break that constraint. It's got to stay on the ground. Flat? Sorry? Maybe L2 is your vertical? All right, so let's do, we got some hypotheses. One is, let's put like L1 straight up and down, but now L2 is sort of like swinging. So there's like option 1. Option 2 was make everything 0, like totally flat. Option 3 was make theta 2 90. Is that right? And my drawing's not great, but something like this. So option 1, like if you have a vertical thing like that and you're pressing down, like technically you don't need any left, right, but now it's like a different system. So we broke like our original kinematic constraint. So that one, we can't do that because now we've got another like free motion. So this one's like kinematically. Disallowed. What about number 2? Cheating? You think so? No? Yeah. It feels, yeah. Something like.
Well, especially like 1 through 3, like R could go negative and then it would be negative.
Yeah. So R could be a negative value, right? Like we could be pulling on R, and that's what happens when it like snaps through. Like next step would be kind of like this. that R is now pulling on it like that. Yeah, but the mechanisms, they move in planar dimension, but they can move like through constraints most of the time. I mean, you can have something where it can't move through the ground, but there's no constraint on that middle link that it can't go past that 0 point. Or even if it did, like maybe it could move like a few centimeters down. So one thing that's kind of weird here is that, like, you're not wrong to say when this is completely flat, R is 0. But if it's slightly less than flat, like 1 degree off of that, then you have a huge force multiplier where it becomes like a wedge, wedging that thing open. So it's going to, at one point it'll require an infinite reaction force pushing it, and then it's going to snap through, and now it needs an infinite reaction force pulling on it. And we do have like a graph, like mechanical advantage. And again, you can read things as things come up and as you want to, but roughly this is kind of what our system would look like as we're getting closer and closer to 0. It would shoot up to like the reaction force that we need went from like basically 0 to almost infinite, like hundreds and hundreds of newtons, even though we're only applying like a 10 Newton down force. Then it would snap through, and now we need negative hundreds of newtons to keep it from flying through, and then eventually go back to 0. So it's not wrong to say like there is a point where there's 0 reaction, but also just from like a stability kind of thing, there's almost no way that you're going to have it at 0. And as soon as you apply any force, it'll move some. And now you've got infinite reaction force. So this one is a yes, but versus down here in number 3. What do you think for that one? Yeah, it does have to be like perfectly, yeah, otherwise it's gonna do some other effect of like snapping down. But we could also take this and let's see if this works. And now, if you like flip it upside down, now it's pretty stable. And this one, if you remember from statics, you remember the term 0 force member? That becomes a 0 force member because everything is like in line with each other. This one, I guess with a check mark, shouldn't it be green, right? These are the important things. Something like that. So if we kind of line it up now, there's no, the force itself is lined directly up with all the supports, and there is no torque being created, so we don't have to worry about it. That one's up to you. Like if you have control over the position and you're just trying to figure out like how do I minimize R, then like with a car jack, you would have pretty precise control as you're like rolling that thing around. If you're thinking of like something that's actually on a roller, like an actual ball bearing, then it would make more sense to be upside down if you want to make R 0, like have 0 force applied. But yeah, it's up to you. I mean, or you could make the case that number 2, like no, number 2 is the right answer because there is a point, there is an infinitesimal point where that statement is true. It's like, yeah, there would be. It would be 0 for fraction of a second or something. Let me just paste. I don't know. I just wanted to paste it in again. All right, so now let's do some math. We did a little bit of thinking about like as this thing is moving, how is R changing? So R can go everywhere. R can be anything from 0 all the way up to like infinity, and it's going to be somewhere in between because we don't have it completely flat and it's not 90 degrees. So it's less than infinity, but it's more than 0. So now the question is, right now, in the way that things are set up, what is R? And I think, yeah, F is 100. R, we don't know. So what do you do to get started here? What is your approach? There's more than one way to do this. So part of it is I just want to see how you go about it. What is it? Why is that? Okay. Yep. So what is this one? Why is that one 166? But how are the forces? Like how are they all adding up? Because they should add up to 0, right? But even still, to make a cut, there should be a total force acting on, unless part of it's moving and part of it's not. it seems like you're trying to break up that 100 Newton into different components. But these two components are perpendicular to each other, so they don't add up. And I don't think it's like I think right now it's less than 100. This one, if it was like a truss structure, you know, not those in it, those can get still. Okay, yeah. This is kind of like average. Yeah, both sides. What are the whole of the bridge? So let's plug in those numbers. Can you add them up? Can you use those to show that the thing's not clumping? So I have anything equals 0. Like a static drop. You take the sum of the forces x, sum of the forces y, overall it should add up to 0. No. Well, you got like reaction forces in there. One that you're missing is that there's got to be something preventing it from like spinning around. So like something pushing up that way. Yeah. That might help some of the. All right, so I did see. Oh, let's get a regular marker back. So I did start to see like, okay, there's gotta be, if I have a pin, I need 2 reaction forces at the pin. There's no torque there because it's not preventing rotation, but it is preventing, that pin can't move left and right, can't move up and down. Then I have F pointing down. I know I have R pointing this way. And then something has got to prevent it from going through that constraint. Like it's can't move down and it can't move up. And when we draw like the whole thing like this, that's it. Those are the only like external forces to those 2 bars. And then we can go through and say, same thing that I was doing in the first problem. Equation 1, equation 2, equation 3. It's like that's always our 3 equations. In statics, they were always equal to 0. In dynamics, we set them equal to changes in momentum, but sometimes that momentum is 0. And in this case it is. Like, it's moving, but it's not moving that fast. So sum of the force is X. Oh, not O. Equals Rx minus R. Super helpful. Sum of the force is Y is Ry plus N minus F. Sum of the moments is that one I'll let you work on. So I'll let you think about some of the moments for a little bit. But so far we know whatever Rx is, like whatever that reaction force is, that's how much our R is, our applied R is. And then we know Ry plus N has to be F, whatever. So Ry plus N total has to be 100 newtons. It's going to be some division of the two. So then what else? So then what's that sum of the moments? What does that one give us? Did anyone approach this differently? Did you have a different thought? Yeah?
I summed up like the X and Y components. I didn't really know it.
Oh, no moment?
Yeah.
Well, here, so a great skill to have, especially for this class, is recognizing like how many equations do I have and how many unknowns do I have. So like how many degrees of freedom does this set of equations have? Right now, I don't know Rx, so there's 1. I don't know R, 2. I don't know Ry, 3. I don't know N, 4. But I do know F. And I only have 2 equations. So I can solve for 2 things so far because I have 2 equations. So I can get 1 more equation with some of the moments, but I still something's missing. We're going to have to do something else. And that's the part that you can go at it in different directions. But we do need at least 3 equations, and then we're going to need another one to, yeah.
You need a moment to I think I got an answer without using any moment.
Okay, what was your approach? Yeah.
The X portion of L1 and L2 has to be equal.
Yeah, let me take a look. All right, but yeah, try something else in moments, unless you want to try a different one. So what is L? So those are okay. So you're doing like a. So the way that you can do that is looking at like because the members only support force along the given direction, then you can create like a free body diagram. At that point where there are like internal forces pushing on the line. So you can have something like that. Yeah. Okay. Yeah, those 2 axes are equal, and then 2 y's. Yep. Yeah. Okay. Then that'll work. Yeah. But it helps to at least like draw that free body diagram. You know you're doing. And that one works great when you only have minis in this. So if you ever have a torque apply, that sort of breaks down something. Yeah, that one. That one doesn't really matter. It changes what the equation is, but it doesn't change the result. And there are ways to make it harder and easier. Usually I choose the origin. Alright, cool. But that is what I was wondering. Anybody was going down that one. Okay. So there was someone in the back, and this is what I was wondering if anyone was doing. If you just look at this point, like right there, because these the bars can only hold force along the bar, and this is specifically because we're not applying like torque on the bar, like it's not a cantilever beam or anything, it's just pins everywhere. Because of that, I can just look at that pin and say this F, this, like, I'll call it like I1, or I is a bad number, but some kind of like internal reaction force. So there's a force from that bar. So maybe we'll call it like B, B1, and then let's do a different angle for B2. So the reactions inside of B1 and B2 have to add up to that total force F down. And that's another way of doing this, where we can look at some of the force. And now we're just looking at a point location rather than total structure. Either way, you're going to get to the same numbers. You'll get to the same results. All right, cool. We're over time. Thanks so much. Yeah. We don't have a right answer yet. All we have is the process. We're like slowly getting there. But I think it ends up being like, oh my god, I can't remember. I don't remember. Yeah. But we're getting there.